BSides DC 2016 videos are brought to you by clearedjobs.net and cybersecjobs.com, tools for your next career move, and Antietam Technologies, focusing on advanced cyber detection, analysis, and mitigation.
Yeah, hi, my name's Andrew Beard. My colleague Ajit Thagarajan is sitting over there in the audience. So we work for a little company called Atomic Mole. Wanted to talk today about detecting malicious websites using machine learning. And I'm really specifically talking about a very specific subset of malicious websites. I'm really focusing almost entirely, and actually totally entirely, on SSL encrypted websites, ones available over HTTPS. So, obvious question is, why focus on those? Encrypted websites are, huge rise in the past couple years. It's easier than ever to get an SSL certificate free or low cost. Make your own via self-signed certificate. The big thing that I want to focus on, if you can actually read it, though, is that part up in the corner, right? This was a slide taken from Dell World 15, which was a conference they had looking at 2014 data. And they were projecting at that point that 50% of all attacks were predicted to use SSL by 2017. So they were saying this in 2015. 2017 is a whole lot closer now than it was then. And everything that we're looking at says that, yeah, they're pretty close to on track. So SSL, there are definitely some benefits, but there are some pretty big downsides to its use too. Especially in the post-Snowden leak realm, users, websites, everybody wants encryption, right? They want to encrypt all the things. I don't want my email being read by anybody, be it a government, be it a malicious individual, be it the company that may be hosting it. We want everything to be encrypted in transit. That's great for users. That's not so great for the guys sitting in the NOC who are used to having content visibility, who are used to being able to see data traffic going forth and being able to tell if there's an executable in a data stream or if this is just somebody looking at Twitter. It's really good news for people who are using the Wi-Fi at Starbucks. Really bad news if you're on the defense side. There are SSL decryption appliances, proxies, man-in-the-middle devices, all of that can be deployed. Has anybody ever actually deployed one of those devices in an enterprise environment? Like a SSL decryption pass-through? Okay, so we got maybe 3 hands. Was that a fun experience for you guys? Yeah, and that's pretty much mirrored the experience of everyone I've ever talked to who's had to deal with one. Trying to manage keys, trying to manage cut-throughs, all of a sudden realizing that you now have the liability whenever one of your employees visits their bank. It's a bit of a pain in the butt. So really want to talk about a lot of those, especially when we deal with that kind of medium enterprise market. Those devices are entirely out of the realm of possibility. So the question is, what can we do? What can we look at in an SSL encrypted stream that can give us some indication of whether this is something okay or if this is something that may be a problem? And a big part of that is the SSL certificates themselves. So this is a DARE-encoded SSL certificate. This is basically a way to represent it in ASCII. If you buy an SSL certificate from a CA and they give you a key file back, this is probably what it looks like. This is what it's going to look like when it's interpreted by, say, your web server on disk. It's not what it looks like in transit, though. When it's in transit, it looks a little bit more like this. And I'm sorry, this is a little bit of an eye chart here. So this is a dump taken from decoding the same certificate that I saw earlier, just running it through base64 to get it in a raw binary format, and just doing a hex dump of it. And you may or may not be able to see there are a couple strings in here that look like ASCII, but they look kind of weird, right? They're very there's not a lot of actual human readable text here. And there are also some what looks like ASCII encoded numerical values there. So if you're just looking at this on the wire and you don't necessarily understand the format of the certificate, you can see there's stuff here, but you don't necessarily know what it means. However, you dump this through the SSL tool that's included as part of the SSL distribution, Open SSL distribution. I believe this is available on pretty much every Linux system ever, packaged as part of Mac OS. Chances are you already have this if you're not running Windows. So you take that same certificate, you do the base64 decode, you pipe it through here, and all of a sudden, now some of this stuff makes sense if you can read the screen at all. You can see here there are different fields, version numbers, different algorithms, validity dates, some of those strings that may look a little bit familiar if you could see the previous one, different algorithms. All this, now you can start associating, all right, there are different key value pairs associated with the certificate beyond just the binary stuff that we saw earlier. There are, so I'm using the OpenSSL binary tool. There are a number of things that can read this. Wireshark, if you look at an OpenSSL exchange where they do a server certificate, we'll be able to dump pretty much all of this info. Bro, really excellent tool, which Liam was doing training on the other day, and I believe is doing it on Sunday as well, can decode this live. But I want to talk about some of these fields in particular. Specifically, these two sets of field, one is the certificate issuer and one is the certificate subject. So in this particular field itself, it's this one here, there are a number of subfields, and you can see things like C equals AU. What that means is the issuer country code is AU, right? It's Australia. The ST, which is supposed to be the state according to the spec, is F2 TEE4, which is no state that I've ever heard of. Same thing with the location, organization, organizational unit, and common name. Common name is more or less the host name of the server in most cases. So these are the fields that we specifically have been concentrating on as part of our research. There's been other research on some of the other fields, the validity dates in particular. There was a presentation at BSides Charm earlier this year by Will Glodek where he kind of looked at those values. So one thing I want to mention, this particular certificate here is actually common to pretty much all of the TrickBot C2 nodes. This was brought up in a paper that Fidelis Cybersecurity published, I think last week before last. Aside from the country code, which is AU, these values look almost entirely random, right? They're definitely not valid countries or locations or anything like that. If you look at them long enough, though, you start and you have a US keyboard, as I do, right in front of me, you can kind of see that all of them are very close together on the keyboard. So what looks like a random string of characters, and you figure is somebody just doing a script, is actually somebody who just went through the certificate generation process and just went do over in different places. And kind of give you some information about who set these nodes up, right? This isn't somebody who has a lot of scripting, who's going who's going to be generating one of these keys or certificates every 30 seconds or so. This is somebody who had a very manual process involved. So this is kind of an example of the kind of things you can get when you look a little deeper into these attributes. So the issuer and subject fields, the ones I talked about, and as we kind of saw in this particular certificate, so they're structured by a convention, right? It's supposed to be that C is a country. It is supposed to be that L is location. That is what the RFC says is going to happen. There's nothing that actually enforces that in any technical process when you do a self-signed certificate. If a certificate authority generated the certificate, or at least signed the certificate, they may check to make sure that those values are good. And if you try to do one that has a location of FE whatever, they may say, no, we're not going to do it, go away. Not all certificate authorities do, but some of the larger ones do, especially when you're going beyond the domain validation certificates. But self-signed certificates are a total Wild West. You can put whatever data you want in this thing, and it is up to the client to try to process it. So I want to talk about a couple of resources that are available and that we use as part of this, and how those pieces kind of fit together. I'll make a little more sense going on. One of them is Project Sonar. Project Sonar is basically a project. It's a project run by Rapid7. It goes out and it scans the complete IPv4 space every 7 days, looking for servers that run SSL web servers on port 443, and specifically on port 443. If you're running something on 8443, they don't look at it at all. They publish data every week. They've been doing it for a little over 2 years now. A little over 3 years now. And so far, they've captured about 82 million certificates. They make all that data available for researchers. You can download them week by week, and they will give you complete X509 certificates in that base64 DARE encoded form that I showed earlier. So a lot of data available there. You kind of got to have to figure out what you want to do with it, though. Obviously, if you're interested in SSL research, this is something that tends to make people salivate a little bit when they think of all the potential stuff. But there's a little bit of work required to actually get something meaningful out of this. Another project is the SSL Blacklist, SSLBL. This is run by abuse.ch, also known as the Swiss security blog. They put out a lot of really good feeds of information, but this one particularly is focused almost entirely on certificates that are used by malware C2 servers. And they're almost all commodity C2 servers. We're talking things like Dridex, Grootkit, Dire was a big one when Dire was still a thing. And they distribute lists of certificate fingerprints, SHA-1 hashes. That's a resource where you can go through and find some known bad certificates. So I'm going to make a couple assumptions here and one hypothesis, and hopefully these kind of prove out, or at least you think they prove out as we talk about things, and you can kind of see how these link up. One is that the internet is really, really big. There are a ton of sites out there. Malicious sites, though, ones that are absolutely done with bad intent, are relatively rare. Now, there's a lot of weird crap out there that isn't necessarily right. I still don't know why I see so many certificates for BlackBerry playbooks available at Project Sonar, but those aren't necessarily malicious unless you've actually used a BlackBerry playbook. So another assumption is the certificate blacklist don't provide anywhere near full coverage, right? Or even of a particular malware family. Even though the internet is really, really big, there's still a lot of bad stuff out there. And if you look at the total number of certificates that are flagged by blacklists, they're really small compared to the problem, right? The SSLBL, I think, has somewhere around a total of 130,000 certificate hashes. And the vast majority of those are for randomly generated Dire servers, which weren't really an issue as of February anyway. So if you went out and you blocked every access to every site on a SSL blacklist, you could pretty much guarantee that you're still screwed, right? It might help you out a little bit, but if that is your sole line of defense, you suck. Sorry. So the other thing is that we can pretty much trust that the certificates that are identified as bad really are bad, and they're really going to stay bad. The kind of certificates that we're talking about on the blacklist are ones that were done with malicious intent, right? That they were specifically generated to use on a C2 or malware distribution server. These generally aren't hijack certificates. These aren't the kind of things where if you are a small electronics manufacturer in South Korea, somebody hacks your website and starts using your site to distribute malware. That's not the kind of stuff that shows up on this particular blacklist, at least. So this isn't the kind of thing where, okay, we're going to clean up your site and you're clean now. In a lot of ways is very similar to what we assume with malware MD5s, right? If it's a bad file, if it was a piece of malware, it doesn't generally become good at some point later. And the last one, which is really the hypothesis. Some actors are going to generate certificates for malware sites, specifically to use for C2 servers, for distribution sites. And a lot of them do it in batches that look similar. And what do I mean by similar? Similar means that they have some identical metadata fields. Some of those fields we were looking at earlier are the same as some other fields that are bad, or are used in certificates that were bad. So with these assumptions, I think we can build a database of certificate metadata that can help us find and track our adversaries better than just using the blacklist, right? It's available in things like Project Sonar and some of the targeting information that we have using the SSLBL feed, and find something that's a little bit better than the sum of its parts. So this is kind of just a general flow here, right? We take information from Project Sonar. Well, number one, Project Sonar spiders the internet. We take information from them. We run it through a bunch of Python scripts and the OpenSSL binary to generate basically a bunch of CSV files, where each row in that CSV represents a certificate that was observed on the internet. And then we dump it into an Amazon Redshift database. Now, we also apply the information from the blacklist to try to label which ones we know are bad and which ones we don't necessarily know a lot about. My CSV files for this look a whole lot like Bro data fields, if you've ever used Bro. That's mainly because when we started this, we were using Bro exclusively. I like Bro. I use it a lot. The first paper we did on this was entirely about Bro. And I mentioned Amazon Redshift here only because it's cheap and it's a Postgres cluster for people who have absolutely no business trying to set up Postgres clusters like me. I think the instance we use costs us about 50 cents an hour, and you can, once you load the data in, shut it down, terminate it, snapshot it, bring it up on demand. So the entire amount of research here, if I wasn't lazy and didn't forget to terminate it at the end of the day, most of the days, probably would have cost us about the amount as 2 or 3 burritos. So wow, that's terrible. So this would be what it would look like if you were looking at our database and you couldn't see it all. This is just kind of overall, each one of these columns represents a separate data field. You notice maybe that most of these are pretty sparse. Most of the certificates on the internet that are coming up through Project Sonar don't have most of the fields. Most of them may only have, say, the common name field, which is right here, which you can see is filled in pretty consistently. So there are definitely ones that have full entries, and this is like this is the location, this is the country code. There are definitely certificates that have that information, but a lot of them don't. And a lot of that is because there are just a lot of devices out there that just have an SSL certificate that just says, "Hi, I'm 10.15.127.8, and that's it. We can't necessarily tell a lot of information about that. So I do want to talk about what we can find and what we can't find, though, because there are a lot of caveats to this. What we can find, the example I mentioned earlier, hijacked or compromised certificates. If the certificate was a good certificate when it was generated, if there was no malicious intent that went into it, there are probably no patterns that we could recognize after the fact, after it was hijacked. If you generated a good certificate for your website and you did all the things that people who generate good certificates do, and then somebody else hijacks it later, that doesn't change the certificate. I can't tell anything about that. This also doesn't really help against targeted attacks, right? If you are, if somebody is coming up with infrastructure specifically to target your organization, they're probably going to do it a little differently than they did the previous time. There probably aren't going to be a lot of patterns there. It's possible, but it's extremely unlikely. This is generally for the kind of crimeware stuff where somebody is just targeting a whole group of people unilaterally. The other thing it's not going to help with at all is initial waves of campaigns. The way that we're looking at things right now, we are using SSLBL as the pointy end of the stick, right? They have to recognize something as being bad first before we can start recognizing if there are patterns there. On the plus side, it does find a fair amount of stuff, though. It finds a lot of certificates that were specifically issued so that someone could distribute malware from it. It finds a lot of commodity malware, Torrent Locker, like I said, Dridex, Dyer, Grootkit, and it finds a whole lot of dumb. When we was looking looking through these, especially when we were looking through them manually, we noticed a whole lot of patterns that just seemed to display a striking lack of intelligence on behalf of the people who are generating these certificates. And I have a couple examples of these later, but I couldn't put in too much. If you're really interested in this, talk to me afterwards, because there's some funny shit in there. So the first thing we started off with, we said, all right, we really want to determine if a certificate is good or bad. We want to give it a binary classification. We want to just say yes or no. So, effectively, we're building a binary classifier model. A very simple implementation for that is just use a logistic regression algorithm. It's an algorithm. It's a very common method. Has a whole lot of implementations available. It's a supervised learning model, but basically what we're going to do is we're going to use that SSL BL data we have to label our data, to say this is bad stuff. We don't know if this is bad stuff or not. Or, we can incorporate some other data to say we're sure this is not bad stuff. So we have an idea of, for a given data set, if it's good or bad, and we can use that to train our model. So our first try was, all right, let's just label some good data using sources like Alexa Top 1 Million, the SSL Notary that kind of rates certificates. Let's just label 5 million certificates and take all the bad certificates we have, throw them into a logistic regression model, and see what happens. So not a lot of good things happened. So we labeled 5 million good certificates. We had 1,335 certificates that were recognized bad that showed up in the Project Sonar data. So this here is a graph of the good certificates versus the bad certificates. See that little line right there? No, of course you don't. Keynote doesn't even render the line. It doesn't matter that the projector sucks. Okay, we're talking about 5 million certificates that we know are good out of a set of 5,001,335. So that means that 99.973% of our certificates were good. And we threw it into a model, and it said it had absolutely amazing accuracy, great fit rate. In a couple of minutes, we realized the problem. Anybody see the problem with this just straight off the bat? No? Okay. So we basically taught our model how to lie. It just said, you know what? Every single certificate in the world is good. There are no bad things in the world. Awesome. I am right 99.97% of the time. We taught computers how to lie. We taught them how to cheat. We may be one step closer to Skynet. If this leads to the enslavement of humanity, oops, my bad. There are thresholds you can adjust with a logistic regression model to prefer false positive versus false negative results. In a case like this, it doesn't matter. You are so far biased towards good results because you've given it so much more good stuff that it's always going to fail. So we learned pretty quickly that you really need to bias your data. You need to split things up in a way that makes more sense to the model. You need to start with data sets where the amount of good things you give it and the amount of bad things you get it are a little bit closer, so that you don't just train it, whole world's good, there's no badness here, and create the eternal optimist computer model. So we thought, okay, let's try something a little bit different. We went on, we tried some other things. Eventually we came to a use case where we said, all right, let's talk about random looking values. Okay, my slide there is missing. Doesn't matter, you guys wouldn't be able to see it anyway. So there were a lot of values that we came up with in terms of the bad certificates that had a lot of random values, specifically in the location, okay, I'm trying to remember. It's the location, the common name, and the organization fields. And when I say random, I mean these were values that were of varying length that had characters A through Z, lowercase and uppercase, and numerical values. And it was very easy for a person to kind of look at it and say, yeah, this is complete junk. It's possible to recognize these kind of things by doing a transformation, right? Compute Shannon entropy on every field and look for certain cutoffs. Say, this is the number of unique characters that appear here. That's kind of expensive to do on every piece of data, not just in our set, but eventually when we want to try to apply this stuff to live traffic, doing it for every certificate that comes across your box. And we really wanted to try to do this without creating more problem-specific attributes. So we took our 1,335 bad certificates, and we labeled them all as random or not. And we came up that 38% of the certificates we had, which it totally says down on that thing you can't see, were random. I do have a slide, and yeah, you totally can't see that. But 38% is a pretty surprising percentage when you're talking about all the bad things that you found total. So we said, all right, let's take this, and in the column here is one that we added that's just called looks random. This was something that a person went through all 1,300 certificates, and they just said, this one looks like it's random, this one doesn't. So we went through and we did a logistic regression model on this too. And this time we found something that was pretty good. We were still in the 95%, and it was giving us for both positive and negative results. So it was able to differentiate the majority of the time whether or not this was something that was a random value that kind of looked bad. The bad news is we started playing around with it, and we started realizing that it was entirely basing it on the state and country codes. So the state codes and country codes most of the time are 2-character values, both uppercase. And so you can say, all right, well, I've got letters, 26 letters, so 26 squared operations each. You've only got 26 to the 4th possible combinations there. So it basically ignored all the other values that we had, the other very long random text strings, and it just said, all right, I'm just going to, based on these 2 values, figure out which ones are common and good and which ones are really rare and bad. There's a lot easier way to do this, right? There's a method called Bloom filters, which are basically a probabilistic way of taking sparse data and creating a filter out of it, saying, yes, it matches this pattern, or no, it doesn't. By using a Bloom filter and just finding out which ones are really, really common country codes, which ones are really, really common state codes. If I have a state that's VK, chances are that's not something good. That's probably something random. And if I combine that with a country code that no one's ever heard of as well, then we have a pretty good likelihood that this was just something entirely randomly generated. This method is a lot less computationally intensive to run with than the running an entire logistic regression model and then evaluating something against that model. Like I said, it's not 100% accurate because we're talking about random values. It's always possible that somebody can generate a US country code at random and combine it with something that's a valid state code, but probability is quite low. So we did some more work. We started realizing overall we were trying to come up with different patterns of things. We were trying to come up with different groups of problems, different groups of bad certificates that we could come out with and find something that was usable. And we ended up just kind of settling on, and we got our best results out of just simple clustering. Clustering is all about counting occurrences of specific values. And we decided, let's just start with the most common values for a given attribute. For the location, what are the common locations? There are, like, say, London, Springfield, York. You look for other common attributes that happen in that same set of results. Okay, what's the country code that generally corresponds with London? Most of the time, it's Great Britain. That one's kind of obvious. But then other ones, like what organizations in our set of bad certificates normally correspond with London? Then you start finding more interesting things. This is a little harder to do with categorical data. And when I say categorical, I mean non-numerical. The word London, just as text, as a word, isn't particularly closer to Taipei than it is Springfield. If these were all numbers and I had something like, I could say 4 and 5 are closer together than 47. So we start with kind of a one-dimensional clustering, which is basically just trying to find counts of values. Then we look at points of intersection with other values and try to find things that are common in our bad set. This is generally an unsupervised activity, just finding clusters of values, but we're specifically going to try clustering in our set of bad values that we know are already bad. So it's still an unsupervised method, but there's some level of supervision that's going to go on when we go to apply the results. So imagine for a second that you take one attribute, and in this case it's the location, which is by L. And pretend you're back in grade school, and you have one of those big things of construction paper and those stupid little scissors that you can't possibly cut yourself with. And you cut a piece of paper out for every value you find. And the bigger the piece of paper, the more common the value is. So I can see here that if I cut this out and I laid all these things on the paper, the most common location I've got is just no location whatsoever. And that kind of makes sense given that sparse table that we showed early on. Most people don't include location, and especially most people that are doing the malicious certificates don't either. But then there are some other values that are very common. Springfield, York, London, Taipei, and there are a bunch of little ones. So we're going to do the exact same activity again. We're going to do it with another attribute, and we're going to overlay them on top of each other. Basically, you're going to come up with a whole bunch of blobs. And this kind of helps represent a little bit what some of the different things that can happen when you do these intersections. For example, this one, Springfield, location Springfield, and organization DIS almost always happen together. These two sets are almost identical. Almost nobody uses location Springfield without using DIS. Location empty is pretty common, but then there's a big section where you've got an empty location and internet widgets P2Y LTD. By the way, anybody know the significance of this string here, internet widgets P2Y LTD? Right. And if you're just clicking through default, then somebody may totally omit location, but still have this guy in here. So this is common all over the place. I'll show this a little bit later. My company LTD, that should sound familiar to a couple people too. Company is a common organization no matter what the location is. So there's no real correlation between these two values. But there is some correlation between my company LTD and York. And Taipei, although the location itself is pretty common, maybe there's nothing that necessarily clusters with that, specifically for an organization standpoint. So we keep doing this over and over again, and we try to find different layers that intersect with each other to make big groups, to make big groups like this. That kind of gives us an idea of what a pattern is. But this just tells us that it's common in bad stuff, right? We still need a way to kind of go and rate this. So we try to do some math around that, right? Overall, the patterns that we have should be more common in the bad certificates than overall, right? If we're looking for bad patterns and we have a set of bad things, we're hoping that we know more about the bad stuff than we do about just looking for the same thing in the internet at large. So we ended up finding a ratio that is number of matches in the overall set, the 82 million, versus a number of matches in our bad set, 1,335. And we normalize that to the number of matches per bad set. So effectively, we're saying for every time that this showed up in the bad set, I would expect it to show up so many times in my overall. If it's exactly 1, then that means that we only ever found it in the bad set, because a bad set is a subset of the 82 million. So it's not really useful, right? We have identified all the cases that we possibly know about where this thing occurs. Doesn't mean that it's not a good indicator. It just means that we've told everything that we can know about it just by specifically looking at the blacklist values. If it occurs greater than 1,000 times, that means that it occurs really often in the overall set. In fact, it may occur more often in the overall set than it does in our little small set. That means it's a pattern, but it's not necessarily one that we want to use, and I'll show an example of that in a little bit. The sweet spot that we found is between a value of about 1 and 250. That's where we find potentially useful stuff. I have some scripts that calculate these values and shoot them out from the raw database in our GitHub. And this is kind of the example, or this is an example output of that script. So what this is basically saying is, all right, I'm going to take one here. I'm going to say, let's say US or Monsanto. Okay, so I found Monsanto as a subject twice in our bad set. I found it 26 times in our overall set. Okay, there may be something there. Democracy, found it twice in our set and 11 times in the overall set. So I'm trying to look at expansion. This one here is the empty, right? Subject O appeared, organization appeared in the subject blank 189 times, and then it appeared, that's a lot of digits. I can't tell if that is 52 million or no, it's 5 million times. But it means that it's incredibly common in the overall set. Just by saying, okay, blank, a blank organization appears in the bad set fairly often. Okay, but it appears everywhere fairly often. So I can't necessarily say that that's an indicator of bad behavior. Once something gets that big, again, Internet Widgets PTY appeared 75 times in our set, appeared 186,000 times overall. It's just a common value. When those high values come up, you can tell, well, there's normally something going on here, and there's some reason it appears often, but that reason is not necessarily maliciousness. But I'm going to take an example of one that is in that sweet spot that we kind of run down. So this one value here appeared twice in our bad set, and it appeared 13 times in the overall set. Has a ratio of 6.5. We say, okay, that means that the algorithm goes to the next step, and then it tries to correlate that with other values. I don't know how much you can see of this guy stuff. So it starts, so it says, okay, based on this particular organization value, I'm going to look for other locations, other organizational units, other serial numbers, other countries. I'm going to try and find every other value that seems to happen in common with this one. And it came up with 7 values. So we can see here, you can't really see it. But it's kind of funny, and this is where I start talking about the dumb stuff. So this value shows up with subject L, Quebec, but Quebec doesn't have a K on the end of it. When Montreal, there's a T in Montreal. This is Montreal. So when you start seeing these patterns, you tend to see a lot of misspellings, a lot of things that look on very casual glance like they may be legitimate, but on a very cursory examination you can see, yeah, this is just somebody who is going really fast, trying to do a lot of stuff, and then totally flubbed it. So down here you can see all the results for the pattern we have here with Quebec, gay team as the organizational unit, Canada as the country, Montreal, and Quebec. And you can't quite see it here. This column is whether or not it appeared in our feed or not. This particular row appeared in our feed. You can see the first two did appear in the feed. So there were two things, and they had a lot of stuff in common. They were almost identical. We searched for these specific values in our overall set, and we found 13 different cases where those values popped up. And after a little more research, it turns out that every single one of these was actually hosting a DriedX C2 server. So, you can generally say, once you start having these weird patterns of things that are fairly uncommon but do expand out, that there's commonality here, and that whoever generated this certificate, these first two, is probably the same guy who generated all these other certificates. They're things that are rare in isolation, but for some reason appear, more often than they should in our bad list. You do that, and now all of a sudden you can find a lot more stuff than you did from that blacklist alone. So, big question, right? What can I do with this crap? So this was my kind of good, better, best, except the okay one isn't really that good. So it's my okay, better, best list. First thing you can do is, as we saw here, you can take your blacklist and you can expand it, right? We found 6.5 times as many indicators as were on the blacklist for that one particular example. And it turns out that page that I previously showed, everything that was in the 1 to 250 save 2 indicators came up with a similar expansion rate. So from this, you can go from having 1,335 indicators that were matches up to tens of thousands, hundreds of thousands pretty easily. So you can make just a better blacklist, one that's based off of inference a lot. You could find stuff there. You could patch that through the same way you do your normal feeds. The better thing to do is to start using those patterns and finding strings in your SSL traffic, and you can do that with a packet-based IPS even. We saw early on those kind of recognizable strings, even in the binary data. There are plenty of snort signatures. I know SID 19551 in particular is an example of one that look specifically for binary stuff in the SSL exchange, and those text strings generally reflect back to attributes somewhere in there. The best thing you can do with this, though, is to just start looking at actual patterns in your network traffic using a tool that can read SSL data. Bro is a good one. There are plenty of other commercial tools that can do similar things. It really doesn't take a big investment to get that kind of contextual awareness and start reading what those values can do for you. You can match against that stuff and find a lot more stuff going on. And I say that looking for it live is so much better than just creating a blacklist because there's a lot of delay in the blacklist, right? If you're doing it off SSL BL, you're based off of what specifically they can see. If somebody generates another certificate with the exact same pattern, hasn't shown up in SSL BL, anything like that, you don't know about it until that entire process falls through. If you look at these things live, you can hit them immediately. So this is the triangle, really pyramid, because it's a two-dimensional figure of pain. I think David Bianco was running around here at some point. There you go. Thank you for the triangle. So when we started, we were talking about feed values, right? And the certificate SHA-1 values are just hash values, right? That's at the bottom of the pyramid. The pyramid is all about how much pain you want to cause your adversaries, or how much pain an individual thing can cause your adversaries. Personally, I want to cause as much pain as possible. I want to see my enemies driven before me. I want to hear the lamentations of their women. So I want to do better than this, right? By kind of working through this process and coming up with certificate attributes, we're really talking about more network artifacts, right? We're talking about things that have much longer shelf lives. We're talking about things that we can predict or at least deal with some amount of change on the adversary's point. They can keep generating certificates all day long with similar attributes, and if we know what attributes they are, we win. So this allows us to have slightly higher quality indicators that we can use. So big takeaways: it's possible to leverage really large data sets with specific indicators, find more general patterns that are more useful than those specific indicators in and of themselves. You got to choose your data sets carefully, though. Right? If you just try to dump everything in and just see what happens, you're probably not going to like the results. And machine learning algorithms overall, they give you insight into your data. Sometimes the insight that they give you is that you really shouldn't be using a machine learning algorithm overall in production. Sometimes they suggest there's something much simpler going on here. Do that instead. And I want to say a couple thanks. First to BSides DC and the staff here, Swiss Security Blog for creating the SSL blacklist, and Rapid7 Labs for providing the project sonar data. Any questions? What's up?
Yeah, were you able to do some statistical analysis of some of the data more broadly, like to see if things like certain certificate authorities were more commonly abused than others?
Yes, I did. Something like that. Except you can't really read it very well. So the main thing to realize is a lot of our data is kind of old. We're dealing with stuff that's from 2013 on. So you kind of got to go time slicing wise, right? When I look at this originally, Let's Encrypt barely registers. But mainly because Let's Encrypt hasn't really been around that long. The one that shows up the most out of the total number of certificates by far is Komodo. They've had really cheap certificate programs or free certificate programs available for a long time, which very much biases it. But 87% of the certificates we found were still self-signed. What's up?
So have you looked at a correlation of information, like external information, for instance, maybe the age of the domain, or what exactly is referred to as far as what it's signed for?
So the question was, have I looked at external information correlated with the certificate information, like age of the domain? I haven't. So far, this was pretty much just taking raw data in, but that's definitely a next step on there. I think a lot of stuff in terms of age of the domain also versus the validity period could be potentially interesting. But we were kind of trying to keep it simple with those textual fields that are all exact match. So we didn't deal with any scalar values whatsoever there yet. What's up in the front? Oh, yeah, sure. If I can find it. There we go.
So when you say look for patterns,
Yep.
scripts to look at lag, or are you talking about processing the logs through something similar to what you're presenting?
So actually, I'm mostly talking about using scripts. So there is, as part of the Brocon presentation that we did last month, we had some kind of example scripts, and that's available on our GitHub page as well. But one of the things that we're looking into is kind of making that a little more flexible, because we ended up hard coding a lot of the values into the scripts themselves. I really want to get something like where I can load in a JSON and have that available as part of the Bro package manager, so that's very easy to import. But there's really no universal format for these kind of patterns as an indicator right now. So I think we kind of need to figure out something to do, and my thought right now is JSON, because it has you have to be able to say this field exists, this field doesn't, and kind of go from there. One in the back over there.
What machine learning framework did you use? TensorFlow or something custom?
So all the machine learning stuff was pretty much just, all of the clustering stuff was entirely custom, based off Python stuff. For the logistic regression stuff, we started off, we had some people working on, I believe they were using R coming in through some Python packages, NumPy and some others like that to do data frames. I ended up just doing it the simple way, and I ended up using AWS ML as a service a great deal, mainly because processing power, when I dumped in all the data, was very, very intensive. Any others? No? Cool. All right. Well, thanks for having us. Oh, and if anybody wants to talk about this later, because I realized I've now chewed up